Okay, welcome everyone. Welcome to this week's One World IAMP Mathematical Physics seminar. As you might know, this is a regular seminar of IAMP. And if you're interested in joining our mailing list, there's going to be a link in the chat that you can click on. Also, you might be interested in our organization, IAMP, so you can also find more information on our webpage. This seminar, as all our seminars, is recorded and you can watch it later on our YouTube channel. All right, so now let's get started with the actual talk. It's my absolute pleasure to welcome here Nikita Nekrasov, and he's going to talk about Qouroboros. Please go ahead, the floor is yours.
Thank you. It's my pleasure and privilege to give a talk at the One World Mathematical Physics seminar. So my title is a made-up word. Qouroboros is, so it's like quantum Ouroboros. So Ouroboros is this concept from various cultures of kind of a circular nature of probably of consciousness. So my goal today will be to say something about quantum mechanics. And specifically about integrable quantum mechanics. So in quantum mechanics per se, we deal with non-commutative associative algebras. Which we usually call the algebra of observables. And in many cases, this algebra comes with a parameter, h bar, so that sometimes you can vary this parameter continuously, sometimes it assumes only discrete set of values. And but in the case, more often than not, there is a limit when this algebra becomes commutative. So this is the classical limit. And then it describes functions on some Poisson manifold. And if the Poisson structure, which you get by taking the limit of the commutator, if it is invertible, then the manifold is actually symplectic and can be viewed as a classical phase space. Right. So when h bar is non-zero, in rare situations, this non-commutative algebra contains a large commutative subalgebra. So this type of problem can be analyzed actually in a kind of an abstract quantum mechanics where one deals with observables but does not deal with states. So these algebras need not be C-star algebras, need not have representations, but of course, in conventional quantum mechanics, we were interested in algebras which are represented by operators acting in some Hilbert space. We have a homomorphism. So endomorphisms of some Hilbert space. And so that then the algebra has to have some additional structure, kind of a conjugation, which maps to the Hermitian conjugation in the space of operators. So the separation of notions, algebra and its representations, in spaces of states is seems to have been realized relatively recently, that one can study algebra separately and representations separately, and this concept is has become kind of more natural in the context of high-dimensional field theories. So it's not really obvious from the quantum mechanical point of view. So this is okay. So what's quantum field theory? What are the quantum field theories which I want to talk about? So first of all, naively, quantum field theory is quantum mechanics with infinite number of degrees of freedom. So you take some lattice model, you have degrees of freedom which could be spins or some variables describing maps of lattice sites into some space with symmetry or without symmetry, and you have degrees of freedom which could also live on links, which are responsible for interactions between spins, so on and so forth. And then you take the limit when the number of sites goes to infinity, with appropriate scaling of spins and interactions. And so the Hamiltonian of lattice model will become eventually the Hamiltonian of some quantum field theory, if you're lucky. I mean, it's not guaranteed. It's just if you throw in just anything, it might not, the limit might not exist. But if you're careful, and if you're lucky, then you might have a non-trivial limit of which will describe field theoretic degrees of freedom, like waves propagating in space-time, and so on and so forth. So in particular, if you think of quantum mechanics as some kind of a theory of random paths on in the phase space, So we want to compute something like integrals over maps of a line or a circle into some symplectic manifold. So then you would write here the path integral in this schematic form. So H is the function of the phase space which is responsible for dynamics, the Hamiltonian. So then the observables, which I was talking about, which form the algebra A, would be kind of a regularized versions of the functions on P inserted under the sign of the integral. And non-commutativity has to do with the subtleties of making sense of this integration. Then the next best kind of approximation to the theory of exploration of the phase space, which seems to come, which comes in a kind of a almost canonically associated to the quantum mechanics two-dimensional theory. So the simplest it will study the maps of two-dimensional Riemann surfaces, and as a target space, I will take the complexification of the phase space. So this is and here I view it not only as a symplectic manifold, not only the symplectic manifold with complex structure and the holomorphic symplectic form, but also with some, I endow it with some metric, with some Hermitian metric. So this is the auxiliary data, which will not affect the properties of quantum mechanical problem, which is hidden inside this two-dimensional model. So here one integrates over the maps of the two-dimensional Riemann surface, and right. So this is a metric G on this complexified space. Then I would write something like G. So the claim, which is not quite obvious, is that this problem, this original problem of quantizing classical phase space in the path integral of quantum mechanics, which is the integral of a paths in some symplectic manifold, is actually contained inside a seemingly more complicated problem, namely the study of maps, of random maps of two-dimensional surfaces into a different manifold, which is associated with to the original phase space by the procedure of complexification. Let me just give you an example of what this complexification does and what kind of space you get. So the simplest example. So So let's take the simplest symplectic manifold is a two-dimensional symplectic manifold. The simplex compact two-dimensional manifold is a two-dimensional sphere. And so this is the it's a round sphere. And we have it has a symplectic form, which is say right where angles. And well, everybody knows that if you quantize the two-dimensional sphere, you get the finite dimensional Hilbert space. And it's a representation of the group SU2. So the group SU2, which geometrically rotates this two-dimensional sphere. It is also well known that if you just look at the algebra of functions on the two-dimensional sphere, let's say that the sphere is embedded into R3, and so functions on the sphere are functions of three variables. Let's say so just some polynomials of x, y, z, modular relation x squared plus y squared plus z squared equals constant radius. So that algebra, let's call it A0, it can be deformed. So this is the concept of deformation quantization. And so this is deformed into the algebra with generators x, y, z, which obey the commutation relations of the algebra SL2. Modular the relation that x squared plus y squared plus z squared equals a constant, again, which we can choose this constant to be anything, and it's depending on how we scale things. So in order to recover, okay, so let's just finish writing. So this is the algebra. It's the universal developing algebra of the algebra of SL2, which just means that it's the associative algebra generated by x, y, and z, obeying this commutation relation. And this commutation relation, as is well known, has a center. So this combination x squared plus y squared plus z squared commutes with everything, so you can set it to be a constant. Now, a crazy fact is that only for special values of this constant that this algebra can be represented in a way which preserves the group, the action of the group of SU2 or SO3. So it means that quantization, understood as a sense of deformation of classical structure, and the quantization which comes with the representation of the algebra of observables, they are not necessarily the same things. So there's something interesting is going on here. So so this is P. This is the classical phase space, and now its complexification is simply it's going to be a complex surface that is to say it's a real four-dimensional manifold. So now it sits inside C3 instead of R3. And so it's a space of, we can describe it by the same equation, but now with x, y, and z being complex. And what is remarkable, which and was discovered by Toriguchi and I think Tom Hansen long time ago. This four-dimensional manifold actually has a metric which solves Einstein equations. And in fact, it's called the it's the first example of the so-called ALE space, asymptotically Euclidean space, also known as the Gucci-Hansen gravitational instanton. And so this type of spaces were generalized by Gibbons and Hawking. So these are four-dimensional manifolds. One can view them as vibrations with a circle fiber over three-dimensional Euclidean space, and these vibrations they generate at a certain number of points. So the Gucci-Hansen case corresponds to the case when this number of points is equal to 2. So this fiber gets smaller and smaller, and over this point it just disappears. So if you connect these 2 points by an interval and look at the fibers over this interval, then you will see a circle which gets smaller and smaller at the endpoints of the interval. So there is a two-sphere, non-contractible two-sphere sitting inside this four-dimensional manifold, and that's the two-sphere which we complexified. So we added 2 more dimensions. So in the studies of two-dimensional of maps of two-dimensional surfaces into this complexification of P, one can consider a special setup in which this surface is a product of an interval times a line. This is sigma. It's a strip. So let me just try to draw the picture. So this was the original two-dimensional sphere. Now it sits inside the space of a twice dimension. This is the complexification of the phase space. And now imagine that I'm studying the maps of a strip such that one end of the strip maps on the same two-dimensional sphere, and the other end of the strip has some fixed boundary condition. A special type of Neumann boundary condition. So it means that this black end, I hope my colors come out right. So it is allowed to be anywhere, but something special is going on at this end. So now you can sort of see the at least one benefit of this picture is that you can sort of separate the algebra and its representation. So the algebra, which might depend on a continuous parameter, sits on this end. So this algebra is generated by operators, observables, which are inserted at the boundary, and they're only consistent with a special Neumann boundary condition. And so the states the states come from the second component of the boundary. More precisely, the states are the strings which connect two types of boundary conditions. Now, one can imagine that inside the space P of C, this complexified space, there are other interesting submanifolds. If you look at this equation, x squared plus y squared plus z squared equals a constant, and remember that x, y, and z are complex. Now imagine that, let's say, x and y are real, but z is imaginary. Then this equation describes not a sphere, but a hyperboloid. It could be this type of hyperboloid or that type of, depending on the sign of the constant, on the phase and sign of the constant. So if I keep playing this game with the red boundary of my worldsheet sigma mapping to some half-dimensional submanifold of P, but the submanifold is chosen a different way. Instead of the sphere, I use some hyperboloid. Then I will get a different representation. So it's the same algebra, which is built on top of the Lie algebra SL2, but the reality conditions are now different, and the representation might be different. In particular, it could be an infinite dimensional representation. Okay, so all this is very nice, except that it seems that we replaced a simple problem of quantizing, of studying this, let's say, representations of SL2, maybe some combinations of those representations, as we do in the studies of spin chains. We replaced it by the problem, which is infinitely much more complicated, because now we have infinite number of degrees of freedom. So how can it be useful? Here is the philosophy. So why it could be useful. So let's just think, how do we compute integrals? So in my original quantum mechanical setup and in field theory setup, so we want to compute the path integral, or maybe a finite dimensional version of this path integral, kind of a oscillatory integral or exponential integral. So let's just think, when something is computable, how does it happen? So how do we actually manage to, oh my God. Okay, how do we manage to compute that? Well, okay, let me be a bit more abstract. So I'm computing an integral of some different, of a top form omega over some space P. So the space P could be the space of paths, could be space of fields. There are basically two cases to which we reduce these computations most of the time. So either we can split P is a union of components, and on each component we know the antiderivative of the integrand, and so then this computation will reduce the sum over I over the integral over the boundary. And then maybe some contributions from the overlaps and so on. But the point is that basically locally, you can split the integration domain into pieces. On each piece, your integrand is a total derivative. So then the integral can be computed. So for example, the simplest type of integral which everybody computes, Gaussian integrals, which are the starting point for perturbation theory in conventional quantum field theory. Let's say, so this is where we know how to represent the Gaussian measure as a total derivative. So the result is the contribution of the boundary in question is a small sphere around the critical point. So that's one possibility. And another possibility is when there is another space, it's a bigger space, interpolation space, Q, with a boundary which consists of the original domain of integration plus something else. And the form omega can be extended to Q as closed form. So it extends to. So then the integral of the original form omega over the original space P is equal to the integral and it may happen that this integral is simpler. So these are the games which I'm going to play. So I'm going to try to modify the path integration domain, and so by embedding the quantum mechanical problem into a quantum field theory problem, one effectively does the combination of these two approaches. Now, the fact that there is a derivative operation, this Durham differential in the field space, this is typically one of the incarnations of supersymmetry. And the fact that this form omega extends to a form omega tilde on a larger space, so you should come up locally. It means that you need to supplement omega with a form of 1 degree less times one form in normal direction. So these additional differential forms in field theory, their role is played by fermions. So typically in these embeddings in the high dimensional space of fields, this high dimensional space of fields is the space of fields of a supersymmetric theory. So so far I kind of reviewed without much detail how we lived from now 1 dimensions to 2 dimensions. So this was quantum mechanics, and this is sigma model. So it turns out that the story does not end here, and in fact, when you think about this type of boundary conditions, which, as I said, one needs to impose in the sigma model, it turns out that these boundary conditions are actually naturally appearing in if you further embed the sigma model into a even higher dimensional theory. And that's, let me just state it without further ado. It's a 4-dimensional gauge theory. So this is supersymmetric. This is also supersymmetric. And this is not supersymmetric. And then one can ask, okay, maybe there is a way to continue this, maybe a gauge theory which without supersymmetry can be embedded into a high dimensional theory with supersymmetry, and there are some indications that that can be done, and so there is some kind of a circular structure to this this procedure. So that's the quantum Qouroboros of the title. Okay. So let me spend the rest of the talk explaining how this works, maybe in a non-trivial but still rather simple example. So what I want to talk about is the type of gauge theory. So let me start now in 4 dimensions. So in 4 dimensions, we start with, let's say, SUN gauge theory with so-called n equals 2 supersymmetry. So let me just write the Lagrangian of the theory. So it contains the kinetic term, Yang-Mills kinetic term for the gauge fields, the theta term. There are scalars, which are superpartners of the gauge field. There is a potential for the scalars, and there are fermions. So this is the minimal set of fields which contain gauge fields and which have supersymmetry, which is generated by 8 odd generators. And so we live in this is on R4 for space-time dimensions. So phi takes values in the Lie algebra SUN tensor C. So it's a complex valued adjoint field. So if you look at this Lagrangian and you ask what are the configurations which have lower energy or vanishing energy. So low energy configurations, and if eventually we're interested in the absolute minima of energy, which is 0 in supersymmetric theory, so we're interested in vacuum. So they are characterized by phi, this scalar phi having non-zero expectation value, which should be such that it minimizes the potential. And so it means that phi can be diagonalized. So this is constant throughout space and time. And so if the field phi starts oscillating around this value, diagonal matrix A1 with eigenvalues A1 and N, then this would cost very little energy, and so this would correspond to massless particles flying around. But the properties of these massless particles, how they interact with each other in particular, depend on this eigenvalues. And so in physics jargon, we say that these are the moduli of vacuum. So it's a highly unusual from the convention, from a mathematical physics point of view situation, when you have a quantum mechanical system with a Hamiltonian, which has a continuous family of vacuum, that is, states which are killed by the Hamiltonian. And so these states are so they depend on the parameter A. Okay, well, so that's the feature of quantum field theory, that if you work in infinite volume, once you fix the asymptotic value of these scalar fields, you get a state which has zero energy, which is characterized by this asymptotics. And if you try to make a transition from that state to another state which has a different value of A, the overlap is 0. So these vacua are orthogonal, and there is no mixing. Once you replace the infinite volume space by finite volume space, like you make space compact, like go on a 3-sphere, then of course these vacua are no longer orthogonal, so there are some transitions between them, and the theory will actually somehow start averaging, exploring all this vacua, and the true vacuum might be one, might be several, but its wave function will be kind of spread all over this modulus. Except that another surprise of the of field theory with gauge fields in particular is that the space over which this vacuum wave function spreads over can actually be bigger. So you see this space C to the n-1, well, it's a complex manifold. In fact, it has a metric this metric is sensed by the massless particles I mentioned, because the effective theory so it's a theory of n-1 abelian vector multiplets, which means that, so these are scalar fields, AI the conjugates, and gauge fields. So these are maximum fields, except that in our world we kind of experience one Maxwell field, electromagnetic field, and in this model you have n-1 different Maxwell fields. You have n-1 types of charges, and so this metric which I mentioned is visible in the form of certain nonlinear interactions between the gauge fields and scalars, and also in Yukawa couplings between fermions and scalars. Let me just write one term in the effective action. So these terms describe the interaction between massless scalars and gauge fields. So in this theory, the effective electric charges of particles depend on the value of A, trivial A. So so here is the picture. So this is the space C n-1, where A is lives, and so it's a complex n-1 dimensional manifold with the special metric G and some additional structures, and inside there are loci where some of the fields become massless. So at least in this loci, the metric G becomes singular. And that's just a breakdown of the approximation of effective field theory. Okay, so where is quantum mechanics and where are the phase spaces? Well, it turns out that if you take that theory and replace and compactify one dimension, so instead of space-time being the four-dimensional Minkowski space, make it a product of three-dimensional Minkowski space times a circle, and the circle could be large. So circle of radius r. It turns out that the parameters of the space of vacuum, instead of shrinking, actually enhance. So in fact, they double. So these additional variables phi come from the holonomies of the gauge fields. Around the circle, and this is the new part. And in 3 dimensions, you can also dualize the gauge field, or if you like, save time in this right now. There is also the magnetic dual gauge field in 4 dimensions. And so its holonomy gives the imaginary part. So let me just remind you that for Maxwell theory, you can do on shell following transformation that the field strength of the Maxwell field solves, since it solves Maxwell equation, its Hodge dual, at least locally, can be written as D of another type of Maxwell field. So this is magnetic dual. So long story short, each point of the original modular space of vacua acquires an additional n-1 dimensional complex torus. So by complex torus here, I mean the quotient of Cn-1 by a lattice of rank twice n-1. So this is the so this is the theory on circle, and the size of this torus is proportional to 1 over r. So when r goes to infinity, when we decompactify our four-dimensional theory to 4 dimensions, this torus shrinks to 0 size. And if conversely we go to 3 dimensions, this torus blows up. So the claim is that this total space, it is actually a complex symplectic manifold. In fact, it's hyperkähler. And so it is actually a complexification of some phase space of some classical mechanical system. And so the computations, and so these computations which use the tricks of integration by part and localization and all kinds of things. So this is localization in the sense of a covariant homology, not in the sense of Anderson localization. Proves that this phase space whose complexification gives the modulus of vacua, it's a phase space of a system of n particles on the line. And so these particles so we denote the coordinates by x1, x2, xn. And the Hamiltonian of this system of particles is the sum of the kinetic term plus interaction term, where this is identification. So this is called the periodic order chain. So these particles they repel each other, but the last one attracts to the first. So it's again, this is kind of Qouroboros structure. And so because of this intricate nature of interaction, they form bound states. So it's kind of clear in the simplest case when n equals to 2, then this is equivalent to the, if you go to the center of mass frame, this is just the Bosch potential. So it's a particle in a confining potential, and so it has some discrete energy levels. So the beauty of the methods which we have developed in the last 25 years in dealing with the supersymmetric gauge theories is such that it allows us to compute the spectrum and the wave functions of these quantum mechanical systems as soon as we identify what is the gauge theory whose module space of vacuum corresponds to the phase space of that quantum mechanical system. And so we have many examples by now. So we have many body systems, spin chains, one-dimensional hydrodynamics, quantum intermediate long wave equation, which interpolates between KdV and Benjamin-Ono equation. And so spin chains, both with finite and infinite dimensional representations, spin representations. And these are systems like Toda, Roger-Moser, and various variations. So it's actually it's a two-way street. So something interesting can be said about these quantum mechanical systems which have been around for many years, but also using this dictionary, we can say something about the field theories, which is not obvious from the field theory point of view, but is kind of obvious from the quantum mechanical point of view. And so it's a useful relation. I apologize. I mean, I tried to give you the gist of the ideas, but I didn't give you many formulas. Maybe it's better.
Thank you. And yeah, we appreciate the ideas, obviously, more than formulas. Thank you. Thank you for a very nice talk. Are there any questions? From the room?
I think everything was clear. If you have any questions, you can email me. I'm sorry, I have to run. We have another seminar, which is
oh, do you? Okay.
Right.
Yeah, in that case, that sounds perfect. Yeah, it's a pity. I mean, it could definitely be a topic for a longer discussion.
All right. So email me. I'm so you have my.
Yeah, well, certainly. Yeah, well, since there are no quick questions and our guest needs to run very fast. Well, thank you for finding time for us and presenting this very nice topic. So let's thank Nikita again.
Okay. Bye-bye. Thank you.
And let's close the seminar.